On the morning of April 10, 1815, in the coastal settlement of Bima on the island of Sumbawa, a Dutch administrator named William van der Hart recorded in his daily ledger an observation that contradicted what would later be written in official colonial reports. The sky, he noted, had taken on a peculiar copper tint at dawn, and the air carried a faint taste of sulfur. His handwriting, normally precise, grows erratic in the margin where he adds, "Bird silent since yesterday. The mountain breathes." Mount Tambora, 60 kilometers to the north, had been rumbling for 3 days. Van der Hart's ledger would survive. Chimpi Hunterbimson, he would not. What followed 4 days later would be documented by those who fled, but the initial tremors, the atmospheric changes, the days before, these exist only in fragments, in crossed-out passages, in letters that reached Batavia months later with sections water-damaged beyond recognition. The eruption began on the evening of April 10th and reached its catastrophic phase on April 11th. The sound, witnesses claimed, could be heard in Sumatra, over 2,000 kilometers away, where British officers stationed at Fort Marlborough initially believed they were hearing naval cannon fire. They dispatched patrols to investigate a phantom fleet. In Batavia, now Jakarta, the explosions were so loud that Governor-General Stamford Raffles ordered troops to prepare for an invasion that never came. The sky turned black for 2 days across an area spanning 600 kilometers. Ash fell like gray snow, accumulating in drifts that collapsed roofs and buried entire villages. The official Dutch East India Company report, dated May 1815, states that approximately 10,000 people died in the immediate eruption. A marginal note in a different hand, added later in what appears to be English script, reads, "Does not account for coastal settlements. Revised estimate unnecessary for record." By June 1815, in the harbor of Surabaya, ships' captains began reporting unusual ocean conditions. The water, normally a clear tropical blue, had turned a milky gray. Pumice stone floated in rafts so dense that vessels had to navigate around them, adding days to standard routes. A captain's log from the merchant ship Wilhelmina describes an island of floating stone encountered on June 18th, approximately 400 kilometers south of Sumbawa, that took 3 hours to circumnavigate. The material, he wrote, glowed faintly at night, as if holding heat from some deep forge. These floating fields would be encountered for over a year, drifting on equatorial currents, slowly breaking apart, sinking, redistributing volcanic glass across the seafloor in patterns that modern sediment cores would later reveal but not fully explain. The ash cloud traveled westward on prevailing winds, circling the globe at altitudes between 30 and 40 kilometers. In London, by late May 1815, the Royal Society's meteorological observers noted unusual optical phenomena at sunset, brilliant reds and oranges that persisted longer than normal twilight. The Astronomer Royal, John Pond, recorded these observations in dry, technical language, time 450, noting refraction angles and duration. He did not connect them to volcanic activity. No one did, not yet. The connection between atmospheric ash and climate would not be understood for decades. What Pond did record, in a personal notebook discovered in 1923 in a Kensington estate sale, was a more unsettling observation. The light quality suggests particulate suspension at extreme altitude. Duration and intensity imply a source of considerable magnitude. Location unknown. No reports received from Mediterranean or Atlantic. In Vermont, on June 8, 1816, 14 months after Tambora erupted, a farmer named Chauncey Jerome woke to find his cornfield covered in frost. This was not unusual for early June in New England, though it was late in the season. What struck Jerome, according to a diary entry preserved in the Vermont Historical Society archives, was that the frost had a peculiar gray tint, and when it melted, it left behind a fine residue that he initially mistook for ash from a distant forest fire. He wrote, "Tasted the water collected from the frost, faintly bitter, examined under sunlight, minute particles suspended, catching light like glass dust." Jerome was not a scientist, but he was meticulous. Over the following weeks, he collected samples of frost, rain, and snow in glass jars, labeling each with the date and conditions. The jars remained in his family's possession until 1891, when they were donated to the Historical Society. In 1968, A graduate student analyzing 19th century agricultural records opened one of the sealed jars and found the liquid still contained measurable levels of sulfate compounds and volcanic glass shards visible under microscopic examination. By July 1816, across New England, Pennsylvania, and the maritime provinces of Canada, the agricultural disaster was unmistakable. Frost struck repeatedly. July 4th, July 9th, August 13th, August 21st. Each freeze killed crops already stunted by cold temperatures and lack of sunlight. The sky maintained a persistent haze that farmers described as a dry fog, not moisture-laden like normal fog, but a high, thin veil that dimmed the sun and turned it a pale disk without warmth. A minister in Williamstown, Massachusetts, Reverend Thomas Robbins, kept meticulous weather records throughout 1816. His entries for July read like a catalog of atmospheric abnormality. July 9th, ice thick as window glass, corn killed, sky the color of pewter. July 10th, no frost but no warming, sun visible yet weak. Wind from the north, persistent, cold. July 11th, rain mixed with something else. Leaves it touches develop spots. The spotted leaves troubled farmers more than the frost. Potatoes, typically hardy, developed dark lesions and rotted in the ground before harvest. Wheat heads filled in completely, yielding grain that weighed half the normal amount. Oats grew but did not ripen. Hay harvests failed, meaning livestock faced winter without adequate fodder. By August, the economic implications became clear. Grain prices in Boston tripled. In New York City, bread riots broke out on August 17th. The city watch records, archived in the municipal archives, describe a crowd of approximately 800 people surrounding a bakery on Pearl Street, demanding bread at pre-summer prices. The baker, a man named Herman Schultz, told the watch captain that his flour costs had quadrupled in 6 weeks, and he could barely keep his ovens lit. "The people believe I am profiteering," Schultz said, according to the captain's report. "They do not understand that there is no grain. Not at any price soon." Across the Atlantic, the situation was worse. In Switzerland, Timon, by late summer 1816, the Rhine Valley regions faced near famine. The Swiss Federal Archives contain reports from canton officials describing desperate measures. In the canton of Bern, on August 29th, the cantonal council authorized the slaughter of breeding livestock, a decision that would cripple agricultural recovery for years but was deemed necessary to prevent immediate starvation. The reports describe roads clogged with families moving towards cities, hoping for relief. One document, filed by a canton clerk named Andreas Müller, includes a hand-drawn map showing migration routes and estimated numbers. Approximately 100 souls from highland villages arrived in Bern between August 15th and August 31st. No capacity for housing. Encampments established outside city walls. Disease expected. In Ireland, where the potato had become the staple crop for much of the rural population, the partial failure of the 1816 harvest created localized famines that prefigured the greater disaster that would come 3 decades later. Parish records from County Mayo describe fields where potato plants grew normally until late summer, then suddenly collapsed, the tubers turning to black mush underground. Father Michael O'Malley, the parish priest of Ballinrobe, wrote in a letter dated September 12, 1816, "The people speak of a curse. They point to the sky, which has not been truly clear since spring. The old ones remember stories of years without summer from their grandmother's time, but they are vague, more legend than memory. What is not legend is the hunger. Families are boiling nettles and grass. The children have the gray look." In Bengal, the monsoon failure of 1816 created a catastrophe that British colonial records documented with bureaucratic precision while offering minimal relief. The monsoon, which typically arrives in June and provides the water necessary for rice cultivation, came late and weak. By August, the rainfall deficit was approximately 40% of normal, according to East India Company meteorological stations. Rice paddies dried, wells dropped below usable levels. The Ganges and Brahmaputra rivers ran lower than recorded in the previous 50 years. A district officer named Thomas Hartley, stationed in Jessore, filed a report on September 3, 1816, that described villages abandoned as families fled toward Calcutta. Level moderate. "The roads," he wrote, "are lined with the deceased, Burial is not possible at the scale of mortality. The heat and dryness preserve the remains in a manner most disturbing. I have recommended to the magistrate that wells in affected areas be sealed, as contamination is inevitable. The cholera outbreak that began in Bengal in late 1816 would spread across Asia and eventually reach Europe and North America, becoming the first cholera pandemic. Medical historians have documented this progression extensively, but what remains less examined is the role of climate disruption in creating the conditions for the disease's spread. Cholera thrives in warm, contaminated water, conditions that the disrupted monsoon and subsequent desperate water sourcing behavior created. Dr. James Jameson, a British physician working in Calcutta, kept detailed case notes throughout 1817 as the epidemic intensified. His notes, archived in the Royal College of Surgeons Library in London, describe symptoms with clinical precision but also include personal observations. The patients speak of the summer that did not come. They connect the disease to divine displeasure. I cannot offer them epidemiological explanations that satisfy. The correlation between climate aberration and disease emergence is suggestive but mechanistically obscure. In China, the Yunnan province experienced severe drought in 1816, followed by catastrophic flooding in 1817, when the delayed monsoon arrived with unusual intensity. Imperial records from the Qing Dynasty archive in Beijing describe the dual disaster in formal language that barely conceals the scale of suffering. A memorial from the provincial governor to the emperor, dated November 1816, reports, "The autumn harvest has failed in 17 prefectures. Rice stores from previous years are depleted. The populace has consumed seed grain. Spring planting is imperiled. Humbly request imperial granary relief and tax remission." The emperor's response, issued in December, granted partial tax relief, but noted that imperial granaries were strained by failures in multiple provinces simultaneously. A marginal note in the archival copy, added by an unknown clerk, reads, "Heaven's mandate questioned in the markets, silence maintained." By winter 1816 to 1817, in North America and Europe, the atmospheric haze began to clear, though temperatures remained below normal. In Geneva, where a group of English tourists had spent the summer indoors due to the relentless cold and rain, one of those confined visitors, Mary Godwin, later Mary Shelley, had begun writing a story about a scientist who creates life from dead tissue. The connection between the volcanic winter and the creation of Frankenstein has been noted by literary scholars, but what is less discussed is how the pervasive gloom of that summer influenced not just one writer, but an entire generation's perception of nature's indifference to human survival. Lord Byron, another of the Geneva group, wrote the poem Darkness in July 1816, describing a world where the sun has been extinguished. "I had a dream, which was not all a dream. The bright sun was extinguished, and the stars did wander darkling in the eternal space." The poem captured something that meteorological reports could not, the psychological weight of a summer without light. In the spring of 1817, as temperatures began to normalize and planting resumed, a different problem emerged: mud. The disrupted weather patterns of 1816 had left soil structures compromised. In regions that had experienced excessive rain, particularly in Central Europe and Britain, the ground had become saturated beyond its capacity to drain. In areas of drought followed by sudden precipitation, such as parts of China and India, the desiccated topsoil could not absorb water efficiently, leading to both erosion and waterlogging simultaneously. A Scottish agricultural reformer named James Anderson published a pamphlet in May 1817 titled "Observations on the Peculiar Nature of Soil Degradation Following the Unnatural Season of 1816. Anderson described fields in Aberdeenshire where the topsoil had separated from the subsoil, creating a sliding layer that moved down slope during heavy rain, carrying crops and fencing with it. "The land," he wrote, "has lost its cohesion. It behaves not as earth, but as a slow liquid." The mud problem was not merely agricultural. In urban areas where streets were unpaved or poorly drained, the combination of abnormal precipitation and degraded soil created conditions that paralyzed transport. In London, the spring of 1817 saw the Thames rise to flood stage 3 times in April alone. The river, swollen with runoff from saturated uplands, carried an unusual amount of sediment that turned the water a thick, brown and deposited layers of mud on the banks and in low-lying areas like Southwark and Lambeth. The Times of London published reports describing streets rendered impassable by adhesive mud of extraordinary depth, and noted that carriages have been abandoned mid-thoroughfare, sunk to their axles, awaiting drier conditions that seem indefinitely postponed. In the American Midwest, particularly in the Ohio River Valley, the spring floods of 1817 exceeded anything in settlers' living memory. The Ohio, fed by tributaries draining the saturated Appalachian slopes, rose over 12 meters above its normal level at Pittsburgh. A journal entry from a riverboat pilot named Samuel Clemens, Time 500ms, not the later famous writer, but a contemporary, described navigating the flooded river in April 1817. The channel is invisible. The river has become a moving lake, carrying entire trees, structures, livestock. The water is not water, but a brown suspension that seems half solid. Our vessel draws 1 meter, yet we strike submerged objects constantly. The mud, when deposited, does not settle but remains in suspension, creating shoals where none existed and erasing channels we relied upon. Navigation has become guesswork. The economic consequences of the mud and flooding compounded the agricultural losses of the previous year. In New England, where families had survived the winter of 1816 to 1817 on reduced rations, the spring planting season of 1817 was delayed by 6 weeks in some areas due to waterlogged fields. Farmers who attempted early planting found seeds rotting in the saturated soil. Those who waited found themselves competing with aggressive weed growth that had been stimulated by the unusual conditions. A letter from a farmer in Brattleboro, Vermont, dated May 15, 1817, describes a carpet of unwanted vegetation so dense and vigorous that our cleared fields resemble pastures abandoned for years. The mud harbors this growth. We cannot turn the soil effectively. Plows sink and stick. In response to the crisis, migration accelerated. Families that had considered moving west, but delayed now, saw no alternative. The year 1817 saw a surge in westward migration that exceeded previous decades. Census records show population increases in Indiana, Illinois, and Missouri territories of 30 to 40% between 1816 and 1818. Extraordinary growth, driven by Eastern desperation. The trails west became muddy corridors where wagons broke down, oxen weakened, and disease spread. A missionary traveling through western Pennsylvania in June 1817 described encountering a continuous train of families, their possessions inadequate for pioneering, their provisions scanty, their optimism forced. The children walk barefoot through mud that reaches their knees. When I ask where they are bound, they gesture westward, as if the direction itself is destination enough. In scientific circles, the connection between the 1815 eruption, time 315s, and the subsequent climate disruption was not immediately made. The concept of volcanic forcing of climate did not exist as a formalized theory. However, individual observers began noting the correlation. In Philadelphia, a natural philosopher named Thomas Cooper published an article in 1818 in the American Journal of Science titled "On the Connection Between Volcanic Eruptions and Subsequent Atmospheric Disturbances." Cooper argued that particulate matter ejected into the upper atmosphere by violent volcanic action may persist for extended periods, diminishing solar radiation and thereby reducing terrestrial temperatures. The article was largely ignored. The mechanisms were unclear, the evidence circumstantial, and the scientific community was not prepared to accept that an eruption in a distant Indies island could affect global weather patterns. Yet the correlation was there. Tree ring data, examined by dendrochronologists in the 20th century, shows clearly that 1816 was an exceptional year for growth suppression across the Northern Hemisphere. Quarries taken from bristlecone pines in California, oaks in Germany, and pines in Siberia all show the same narrow ring for 1816, indicating severely reduced growth. Ice core samples from Greenland and Antarctica contain distinct sulfate layers corresponding to 1815, confirming the global dispersion of Tambora's ejecta. The evidence was archived in natural records, waiting for future scientists to develop the techniques to read it. By 1818, conditions had largely normalized, harvests recovered, temperatures returned to expected ranges. The atmospheric haze dissipated. The mud dried, leaving fields altered but workable. Yet the memory of those years persisted in ways both obvious and subtle. The migration patterns initiated by the crisis permanently altered the demographic distribution of North America. The cholera pandemic that began in 1816 continued through multiple waves over the following decades, reshaping public health policy and urban planning. The agricultural techniques that failed in 1816, monoculture dependence, inadequate storage, lack of diversification, began to be questioned, leading to reforms that would not fully materialize for another generation. In literature and art, the influence of the volcanic winter extended beyond Frankenstein and Byron's poetry. Painters of the period, particularly in Britain and Germany, began depicting skies with unusual color palettes, vivid reds and oranges at sunset, heavy atmospheric effects that seemed almost apocalyptic. J.M.W. Turner's work from the late 1810s and 1820s shows this influence clearly. His painting The Eruption of the Soufriere Mountains, time 500 years, completed in 1815 but extensively reworked in 1817, depicts a volcanic explosion with a sky that seems to glow from within, ash clouds that dominate the composition, and a color scheme that suggests Turner had witnessed or heard descriptions of extraordinary atmospheric effects. Art historians have noted that Turner's sky colors during this period are unlike his earlier work, more intense, more varied, more unsettling. In the archives of the Dutch East India Company, now housed in the National Archives in The Hague, there exists a peculiar document dated 1822. It is a revised casualty estimate for the Tambora eruption, prepared by a clerk named Peter Van Horn. The original estimate of 10,000 deaths has been crossed out. Next to it, in careful script, Van Horn has written, direct casualties from eruption, approximately 71,000. Indirect casualties from subsequent starvation, disease, and climate-related failures in Southeast Asia, not calculable, but estimated in excess of 200,000. Global mortality connected to climate disruption of 1816 to 1817, unknown but substantial. Below this, someone else, the handwriting is different, the ink fresher, has added, report suppressed, correlation too broad for official acknowledgement. File for historical record only. The question of total mortality from the Tambora eruption and its climatic aftermath remains unresolved. Direct deaths from the eruption itself, pyroclastic flows, ashfall, tsunamis triggered by the collapse of the mountain, are estimated between 71,000 and 100,000. But the indirect deaths from the subsequent year without a summer and the cascading failures that followed are impossible to calculate with precision. Famine deaths in Europe, North America, and Asia, cholera deaths throughout South Asia and beyond, deaths from displacement, exposure, and desperation during the migration waves. These numbers exist only as estimates in regional records that were never comprehensively compiled. Modern historians, working with demographic data and mortality records, have suggested that the global death toll attributable directly or indirectly to Tambora may have exceeded 1 million people. But the data is fragmentary, incomplete, biased toward regions with better record-keeping, and complicated by the time lag between cause and effect. What is clear from the archival record is that the disruption was global, simultaneous, and largely uncomprehended by those experiencing it. Farmers in Vermont had no way of knowing that their frost-killed crops were connected to an eruption in Indonesia. Colonial administrators in Bengal could not have understood that the failed monsoon was linked to stratospheric ash from a volcano they had never heard of. Swiss villagers fleeing failed harvests did not know they were part of a worldwide climate catastrophe triggered by a single geological event. The connections existed, but the framework for understanding them did not. On June 8, 24, a climate scientist at the University of Rutgers examined ice core samples from Greenland, looking for sulfate signatures from historical volcanic eruptions. The core section, corresponding to 1815, showed a sulfate spike of extraordinary magnitude, approximately 50 kilograms of sulfur dioxide per square kilometer, one of the largest volcanic signals in the past millennium. The scientist, Dr. Emily Hartman, noted in her research log that the Tambora eruption ejected an estimated 60 megatons of sulfur dioxide into the stratosphere, creating a sulfate aerosol layer that persisted for over 2 years. For comparison, the 91 eruption of Mount Pinatubo, which caused measurable global cooling, ejected approximately 20 megatons. Tambora was triple that magnitude. Dr. Hartman's research, published in 24, also noted something that historical records hint at but never explicitly state. The eruption occurred during a period of already cool global temperatures, part of a climatic phase called the Little Ice Age. The volcanic forcing added to existing cool conditions, creating a compound effect. It was not just that Tambora caused cooling, time 500ms. It was that Tambora added catastrophic additional cooling to a climate already stressed. The historical records show this indirectly, references to old-timers remembering previous harsh summers, mentions of marginal lands that had been abandoned and then reoccupied during warmer decades, now abandoned again. The year without a summer was not an isolated event, but a climatic threshold crossed, a system already under strain pushed into failure. Today, climate scientists study Tambora as a natural analog for understanding sudden atmospheric perturbations. Geoengineering proposals to combat global warming by injecting sulfate aerosols into the stratosphere, so-called solar radiation management, use Tambora and Pinatubo as calibration points. The 1816 climate response is a dataset, a natural experiment in atmospheric modification at scale. The human suffering that accompanied that experiment remains in the historical record, a reminder that atmospheric interventions have consequences beyond temperature graphs. In Sumbawa, the island where Tambora is located, the villages destroyed in 1815 were never rebuilt. The caldera left by the eruption, a depression 6 kilometers wide and 600 meters deep, remains visible, a geographic scar. The ash deposits from the eruption are still present, buried under subsequent layers of soil and vegetation, detectable in soil cores as a distinct gray band. Local oral histories preserve stories of the eruption, though after 2 centuries they have acquired mythic qualities. Tales of mountains that exploded, of darkness that lasted for days, of ancestors who fled and never returned. The historical specificity has faded, but the sense of catastrophe has not. If history is written by survivors, then the year without a summer is a story told by those who endured, adapted, and moved on, often without understanding what they had survived. The connections between a volcanic eruption in Indonesia and frost in Vermont, between stratospheric ash and Irish hunger, between atmospheric opacity and Swiss migration, these connections were invisible to those living through them. Only in retrospect, with global data and climatic understanding, do the patterns emerge. The year 1816 was not an isolated agricultural failure, but a planetary event, a reminder that Earth's systems are connected in ways that exceed human perception, and that disruptions in one system propagate through others in cascading, unpredictable ways. The mud that followed the year without a summer has long since dried and dispersed. The fields that became impassable in 1817 have been plowed for 2 centuries since. The families that migrated west established communities that became cities. The hunger that gripped multiple continents faded. Time 400 years, as weather normalized and harvests recovered. But the event left traces, in tree rings, in ice cores, in parish records and ships' logs, in poetry and paintings, in the collective memory of a generation that experienced a summer that never came and a mud that would not dry. The Earth remembers, in its strata and its ice, what human records only partially preserved.